recording, and we'll see how it goes. So now we're going to start our next section, which is on electric fields. So there's quite a break here. This is a different section. We're going to start. We'll do 4 chapters basically on electrostatics. We'll do another 4 chapters on basically magnetism and electromagnetism. That'll lead us to light, and our final 4 chapters will be on light. So there's a very logical progression. We're going to continue using waves throughout. Question or comment?
Since this is a departure, is this going to be covered on the first test?
So it is on the first test. We'll see how far we get. So on the first test. So let me get my... oh, yeah, okay. So here's an interesting thing. So early experimenters found that there was 2 types of charge. So this thing called electricity, electrostatics. They'd seen it in lightning. They knew it had energy because it could burn trees down. They would, I'm sure they'd get shocked occasionally. You tend to get shocked when you use friction. We get it a lot in modern life because we have a lot of man-made fibers. And so just the process of walking across a nylon carpet will tend to remove electrons or add electrons. And so when we touch the door handle, we can get a shock. You don't see it so much in the South because we're humid, but in Boston every winter you would just get a shock every time. Well, not every time, but very often when you walked across a rug and then went to touch a door handle, you'd get shocked. But even before the advent of modern fibers, there's certain combinations of things, insulators, which when you rub them together will cause electrostatic charge to build up. What's going on? You're taking the electrons from one of them and giving it to the other. So you've got an excess of electrons on one material and you've got a dearth of electrons on the other material. And, it might be weird, but for instance, silk with a glass rod seems to work quite nicely. You can imagine a magician, silk with a glass rod and then shock somebody, that would be quite shocking. How can he do this? The other one is rabbit's fur and ebonite rod, and going to the trouble of skinning a rabbit so you can actually, I wonder if this is going to cause electrostatics. Let's skin the rabbit. It just seems a bit off somehow, but they did. And so they knew about electrostatics, and they could store electricity in little jars. They had Leyden jars that they could charge up and they could store electricity. They learned to build some basic machines. They coincidentally were able to draw the electrons out of materials under vacuum with high voltages. Again, why are they doing that, And they could see the glow of the electrons as they went their way through the gas. And so they had these things called cathode rays. Didn't know what they were, but they knew that they could bend them with magnets. And so they were fine. And then finally, it's an electron. It dawned on them. So there are 2 types of charges, positives and negatives. And what they realized pretty early on, find my pen, what they realized pretty early on was there was 2 charges. Let's call them positive and negative. Is the really weird thing. And they had the equal amounts of charge. Here's the really weird thing. They're made from completely different stuff. What we now know is a positive charge is basically a proton, and it's basically 2 up quarks and 1 down quark. And an electron is a lepton. It's a fundamental particle in its own right. So quite why they have exactly the same amount of charge is just amazing. But they do, even though they're different things. What they found was when they had opposite charges, they attracted. When they had similar charges, they repelled. It didn't matter whether they were similar positives, similar negatives, they repelled. There was another little thing in there, which is if I have a charged rod and just an insulator, doesn't matter what charge it is, and an insulator, I can get a attractive force. That's called charging by polarization, which is kind of interesting. So they played with these things and trying to find out more and more about them. It's always confusing when you're in that stage because you don't really know what's going on. And then along came Millikan, and I'm not being funny, but Millikan was like one of the first American scientists to really get respect in Europe. Now, there were American scientists from the very beginning. Benjamin Franklin was quite a remarkable scientist. Benjamin Franklin went so far as to invent a lightning rod and published it. And because he was a colonial rebel, the British establishment did not like the fact that he could invent something. So they said, we did it first, and hurriedly changed the design so it wasn't identical, but ironically made it terrible. So they clearly didn't know what was going on. But he got very little credit. In all my schooling, I was never mentioned. Benjamin Franklin was not mentioned. There was something about, he said to have flown a kite and hung a key off it and realized that lightning was electricity. He said, but everybody else who tried it got electrocuted. So, there's this big he said rather than he did, he said, so. So this is a kind of interesting experiment. You basically take oil, like a sewing machine oil, a very low viscosity oil, and you put it in a bottle, and you connect that to an atomizer like a perfume spray, and you spray out very fine particles of oil. And actually, just because of the friction, you will rub some electrons off some droplets of oil, so they'll be positively charged. And because there's electrons on this nozzle, another droplet might get that extra negative charge. And so some of these will be positive and some of them will be negative, and a lot of them are just neutral. They're so small. Now, what do you remember about your physics one? If I jump off the Empire State Building and my pet mouse jumps off the Empire State Building, who's going to have the bad day? I'm going to have the bad day, because by the time I reach the ground, what's my speed going to be? 150 miles an hour. Actually, I reached that relatively quickly. Actually, by probably, 20 stories I'm at that. I'm probably at terminal velocity for quite a long time on my fall. And my terminal velocity is about 150. Anybody remember, I don't need to know the number, but anybody remember, will a mouse have a bigger terminal velocity than me, a lower terminal velocity than me, or about the same? It's much lower. So the mouse reaches its terminal velocity really quickly, and it kind of like it. I'm sure it's anxious on its way down, but it actually hits and is said to be able to scamper away at the end of it, if only with a slight limp. But do not try this, please don't. But smaller objects reach terminal velocity, and it's a much lower terminal velocity. So these guys have a terminal velocity that's really low, and they reach it really quickly. So they basically float around. But gravity does pull them downwards. It's not that gravity is turned off, it's just that they have a steady, constant velocity rather than an accelerating velocity. Let's put a hole in the floor, and so a few of these guys will stream through. Let's look at these guys, so let's put a lamp in here so we get light reflected off these guys. Let's look at them carefully, so let's put a microscope in here so I can look at these little droplets. And let's play with them. They've got charges on, so let's put a battery in here and make, say, the top positive and the bottom negative. And what that will do is a negatively charged object, oil droplet, will be attracted upwards, say, or at least its rate of fall will decrease. A positively charged will be attracted downwards even more. Neutral will just continue. And so this is a experiment that pretty well every physics major does, and it's probably a 4-hour to 8-hour experiment. The trick is that you pick as many droplets as possible, and you drive them up and you drive them down and you time them, and from that motion you can tell their charge. You do comparisons between how quickly they fall and how quickly they're driven down and how quickly they're driven up. Yes?
I thought you said that was a vacuum chamber.
No, it's got air inside. Oh no. Before, people did work with vacuum chambers, but not this. So this just has air inside. So basically you drive them up and you drive them down, and you can time them and you can figure out what the charge is. And you do not get the answer of 1.6 times 10 to the minus 19. You don't. You will get an answer, and you'll get another 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 answer, and you get another answer. And if you're smart, you'll get 100 answers. And you'll start doing subtractions. And what you'll find is that, because this is what's going to happen, this might have 7 electrons on it, and this might have 5 electrons on it, and this might have 11 electrons on it, and this might have 13 electrons on it, and this one might have 6 electrons on it, and this one might have 19 electrons on it. So the chances of getting an oil droplet with 1 electron on it is really tough. But by doing enough of them, you can get to the stage where you say, what's the shortest, the smallest difference? And you say, oh, look at that. And you find that when you get that, you get 1.6 times 10 to the minus 19 coulombs. So the inference is that's the charge of 1 electron. And people have done this thousands of times, and they've never got smaller than that. And so that's what we take as the charge of 1 electron. Yes?
How do we get this whole value of C, this charge? Like that, 1 meter was...
You just look at these guys and you go, this floated down, so that indicates its mass. I get the speed of floating down, and I can use that to indicate its mass because I know its terminal velocity. And then once I know its mass, I can see, well, I've driven it up at a certain velocity, so there must be a certain driving force on it, and I can figure it out from that.
Is the force, the electric?
No, the C is the amount of charge, but you can use an interpretation. We've not done the physics yet to be able to do that interpretation. Yeah. Yes?
I think you refer more to what's the definition of C? Like, for example, meter is how much light moves through specific time.
Yeah, and how like a
So
kilogram
how do you
is,
measure C?
a liter
C.
or 4 degrees Celsius.
C for charge.
It's a coulomb.
How do you define a column?
It's 1.6 times 10 to the minus 19.
How is it?
How do you...
It's actually, it's, oh, I see what you're saying, I'm sorry. If you get a current flow of 1 amp flowing for 1 second, that is 1 coulomb.
Okay, so a coulomb is 1 amp per second.
1 amp second.
1 amp second. Oh, okay.
An amp is 1 coulomb per second.
Right, okay, I understand. All right.
So it's kind of like a complicated, so think of it as like mass. It's an amount of stuff.
Yeah.
Yeah, okay. And it comes in quantized packages, which is not necessarily, in theory, yeah. So charge comes in quantized packages. Do you think mass does?
Sure.
So,
It's the weight of a neutron and a proton.
oh, you can get less than that.
Quark.
So is the quark the smallest thing you can get? We don't know of any particles that are smaller than quarks, but is that the smallest mass? Could I somehow imagine getting a quark and cutting it in 2? So then I can get less mass than the mass of a quark. So can you see how there's like this issue here about what is quantization? We have this idea that there's this smallest building block. But, you can break a brick in 2. So is that the smallest? And there's strong idea in science that things are quantized. You get one or you get none, and there's nothing in between. That comes from a whole bunch of different areas. But can you see how that was really frightening when people first had the idea, and as it possibly could be applied to more and more classical things, we get uncomfortable with it. So question or comment?
I was was easily thought of as something that's just like a point in space that is.
Yeah, but it's got properties.
Yeah, a point in space that has properties that's not actually like a ball.
Yeah. So yeah, and that's our model. Our models, you know, I had a professor who came in and said, "You'd be amazed at how many people believe in electrons."
Yeah.
And it's like, I believed in electrons, and I thought they were little balls, and he was trying to get across the fact that sometimes we regard them as fuzzy clouds, and sometimes they're like particles, and you know. So the model, yeah, that's exactly right. Whatever works at that time is what we use. So don't get literal. But, you know, quantization either exists or it doesn't, so, you know. Yes.
Aren't particles just disruptions in the field?
I'm sorry?
Aren't particles just disruptions in the
So a field theorist would say that. You know, I think a particle physicist would turn around and say, I kind of like particles, you know. It's like, again, it's whatever works, you know. There's no point in having a complicated model for a simple problem, and there's no point in having a simple model for a complicated problem. So that's, you know, you use the right thing for the right. But don't like I did, when I found out that a lot of things they taught me in Physics 1 weren't true, I kind of felt really resentful. You know, I felt like I'd been lied to. I remember the first time reading a textbook and realizing that there was a mistake in it. And I went around for weeks not believing anything I read in textbooks because they lied to me. And it's like, it was a mistake, that's the first thing. And then the second thing is, even if it wasn't a mistake, even if it was an oversimplification, it's like, you know, models, you don't want an incredibly difficult model so that you can, you know, cook an egg, you know. So you do appropriate models. Oh! I'm using PowerPoint at the minute, so this is kind of cool, as long as I've got sound.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So there we have it. It's a nice little 1 minute video that explains some of that. So we have charges coming positive and negative, and we got them by friction, actually, rubbing a rod against a piece of cloth. So here's my visualization. This is an insulator. It's an insulating ball. Probably, these days we'd probably use polystyrene, but traditionally they'd use pith balls, which were, I believe a pith ball is actually made from pith, and pith is actually, I could be completely wrong on this, it's just, but I believe it's basically it's a fibrous compound, fibrous material, and I think it was originally made from the pips of oranges. It could be completely nonsense. Maybe my physics teacher was having a joke when he said it, but I've never looked it up. But it's a light insulating material. And so we have our rod that somehow got charges on it, and I rub my rod against the material, and it's like buttering cold toast with cold butter, in that it's not nice and smooth. You end up getting bits of charge haphazardly on the surface. And it leaves a very unsatisfactory distribution, because if you're here, you feel a strong electric field maybe pushing away. Maybe you're a positive charge, and you feel a strong field pushing you away, and round here there's next to no effect. So from an experimentalist point of view or from a teacher's point of view to try and demonstrate what's going on with this, it's a real pain. You tend not to want to use it. However, take that same idea. Oh, I didn't mean to do that. Take that same idea and get yourself a nice piece of insulator and spray charge onto it. Somehow. Well, a needle is a really good way of spraying charge. Or crudely rub the charge on it. The charge will stay where the charge is. So let's say that's all positives. My pen's not doing so well. And then you get a salt shaker full of some pigment, a nice insulating little powder. And what will happen, you'll be amazed to find out, well, I would be anyway, you'll be amazed to find out that the powder will tend to stick where the charge is because of the polarized effect, and it will tend not to stick where the charge is not. And then you put it through a heat press to bond the particles of powder to the page so it doesn't rub off. And what have I just invented? Photocopier, isn't it? That's kind of how photocopiers work, yeah, crudely. That's kind of how they work. They work on the principle that you have an insulator and the charges stay where you leave them. And you don't want them bleeding around. So what is a bit of a pain as far as demonstrating electrostatics is concerned is a whole industry that we use all the time. So, you know, there's always an up and a downside. As I say to my wife, stubbornness is also tenacity. So when I do a good thing, I'm tenacious. When I do a thing that's not particularly liked, I'm stubborn, you know. Not that you need to know that, but... You know. So anyway, from a demonstration point of view, I'd like to have a better way of doing this. So what I do is I take a conductor. Problem with conductors is they allow charges to flow around. If I have a conductor resting on the ground or on a conducting table, and I put charge on it, that charge will just go to Australia. It will just go away. I've got to somehow trap the charge on my experiment, so I use an insulating stand. Now whatever charges I put onto this conductor cannot escape the conductor. I spread my charges, but now my 4 charges get as far away from each other as they can. Now, in truth, they'd form a tetrahedron, but if you get as far away from each other as they can, and there's a nice uniform field that I can see and predict what's going to happen with. Yes?
So it's like at work I've got like a magnet tray for nuts and bolts. It's like a rubber bottom with a magnet in it and then a steel tray on top.
Yep.
And so anywhere on the tray is magnetic.
Yes.
But if you separate the two,
Yes, yeah. It's okay. A bit like that. Yes. We have that. So we'll do we do demonstrations. This is the bit, I've got 5 minutes for this, so let's just go through it. So don't be hidebound by the letters. I prefer to say F is equal to KE little q, big Q over the separation squared, because there's usually a small charge and a big charge. I wrote this, so I said QA, QB. In the book it probably says Q1, Q2. It's just, you know, you don't get confused because you're wearing sandals rather than shoes. You kind of know where they go and you know how to use them. So don't get tied bound by the exact writing. In this, good old Coulomb did pretty much what Newton did. Newton looked at the moon and the earth, and he said, I think the force due to gravity depends upon the mass of the moon and the mass of the earth. And as the moon gets more massive, I expect the force to get bigger, so let's put the mass of the moon on top. And as the earth gets more massive, I expect the force of gravity to get more bigger, so put the mass of the earth on the top. And the separation, well, as I separate these two things, they will have different forces. Otherwise, then it would make no difference how far I am away. So Pluto would pull just as strongly as the moon pulls. But the moon's a lot closer. So it can't be that distance makes no difference. And it certainly can't be that the further you are away, the bigger the pull is, because otherwise Pluto would be pulling me off my chair, because it's a long way away. So it has to be that as you get farther away, the pull of gravity falls off, and so we put our separation underneath. And then we do some visualization and we say, you know, if this is my Earth, this pull of gravity kind of has to spread out over bigger and bigger spheres, because it's still there. It's just, you know, I'm not adding gravity or losing gravity. It's just spreading out over bigger and bigger spheres. And the area of the spheres go as 4 pi r squared. So that means the thickness of my paint, if I want to imagine it as thickness of my paint, imagine that you take a bucket of paint and you pour it, you paint it on a small sphere, so it's quite a thick layer of paint, and you spread it on a bigger sphere, so it's a thinner layer of paint. So my intensity is kind of like the thinness of my paint. As my separation, as my distance gets bigger, so my thickness gets less and less. As my separation gets bigger, so my intensity gets less and less. And so if I double the distance between the planets, I expect 1/4 the force. And if I triple the distance between the planets, I expect 1/9 the force. So I want an r squared there. So I'd like to have an equal sign rather than a proportional sign. So just putting in a number of a constant of proportionality, which depends upon your units and the physical world. And so we get this. This is Coulomb's basic law. It's basically for magnitude. It's not for it's not for the vector. And we'll review this again next time and do a bit more on this next time. Okay?
It's a lot like gravitational attraction.
It's very similar to the gravitational attraction. Yes.